All right, so now we move on to lesson 8 of Unit A, and that is dealing with vector addition components. Now, this is going to be really radically different than what we've talked about before in terms of when we looked at our original material from lesson 7 dealing with vector addition. Well, what we did is we either added collinear vectors, which simply meant we took two things that were along the same plane, or things that were like an east vector plus another east vector. We took two things that were like this and put them together tip to tail. We also did things that were like east-west or north to south, so we could have also had vertical things. But what we also did is we added perpendicular vectors, and we added things that were, let's say, going east and then going some amount north. And when we put these things together, we got some sort of overall resultant, like the following. So we got some sort of resultant, which I would classify as R. But what happens if we try to add vectors that aren't collinear, or they don't include this right angle triangle, or at least off the surface? Well, that introduces the fact that we now are going to talk about things involved in lesson 8 where seemingly it looks like it is not a right triangle, but we're going to try and force it to have this right angle so that we can do it in terms of the vector addition that we've done in lesson 7. So it's applying a slight contextual piece that's a little bit different, but when we actually break it down, you're going to see that it's very, very similar to the content that we've done before. Now, let's suppose we have the following example here. Mr. R walks 20 meters to the east and then 15 meters in the direction of 30 degrees north of east. Well, you would look at this diagram and be like, okay, well, we can see that the resultant is where we have a start position here. So I'll indicate that this is our start position over here. I'll indicate that this over here is our ending position. And if this is our start and this is our end, well, we can clearly see there's going to be some sort of overall resultant displacement, but what we can't determine is how much does it go east, how much does it go north in order to get there, and what is that specific resultant based on this, because there isn't a magnitude listed right here. Like, I don't see anything listed as a magnitude for the resultant, so clearly I have to solve for it, which means we're going to have to do something with this over here, this not right angle triangle or this non-right angle triangle, in order to figure out what we can get here. So let's take a look at how we can actually take a look at the triangles that look like this and make them look more familiar to the material that we did in lesson 7. Now, before we go into that, if the triangle does not have a right angle, we can't just simply use Pythag. We would look at this and be like, there's nothing on here that indicates that I can simply just do a opposite over adjacent to get a specific angle for the resultant, and then do Pythag in order to get the overall resultant displacement, which would be this hypotenuse value here, or this longer value from start to finish. So when we're looking at this piece here, to find the resultant displacement, we could use a physics 30 skill and use the laws of sines and cosines. And this is actually something you learn in both Math 20. So I'll even write this in here. You learn this in both Math 20. You also learn this in Physics 30. So whatever course you're going to see this in first, you could use this. However, realistically, what we're going to do is actually do the component method. So to solve these problems, we have another approach, and it's the component method. The component method means we're simply going to decompose these or break them apart, break these triangles into perpendicular components of north, east, south, and west. And again, down the road, you are definitely going to deal with this in terms of Physics 30. You will deal with the laws of sines and cosines, but this is a Physics 30 concept. And so until you get there, maybe what we'll do is we'll just keep it simple and do the component method. But if you're interested, you can go on D12 and just look under the useful stuff. I'll have it linked there. Now, let's look at vector addition component method using this component method. So I should rephrase that. Vector addition using the component method. There we go. Now, here's a simple diagram of the triangle that we were just dealing with on the previous page. We know our end goal is to solve for this resultant, or the resultant vector that runs along the main piece here. But in order to get this, what we're going to have to figure out is how much does it travel in the east direction, how much does it travel in the north direction to figure this out. Now, what we're going to do is we're going to take this B vector, or the vector denoted by the green highlighter here, this 15-meter vector. And we're actually going to break it apart using the methods that we've learned in trigonometry from Math 10C. So let's actually just draw this out here. Originally, what we have is that green line, but it's composed of two different things here. It's composed of some amount east, and it's composed of some amount north. And what I could call this is I could even call this like displacement in the y direction, and I could talk about this as displacement in the x direction if I really wanted to. Now, drawing this triangle below, here's what we're going to have. if I draw this triangle, maybe I'll draw the triangle in black as it follows here, and I'll shift it just up a little bit so that we can make sure it fits in everything here. So there we go. There is our triangle. Now, on the inner side here, we know that this was 30 degrees from the vector B. We also know that the length of this vector B was 15 meters. So I'm going to put 15 meters here. Now, in order to get this displacement in the x, or what I'm going to call dx, and in order to get the dy, or the displacement in the vertical direction, aka the north direction, we're going to have to use a little bit of trigonometry here. So if I'm looking at this, I see this as 30. From the 30-degree perspective, we have opposite over hypotenuse. And so in order to get dy, I know that I'm going to have to do the sine ratio, or more importantly, I'm going to have to go sine 30, which is equal to the dy divided by the 15. Now, this means I'm going to have to multiply 15 to both sides, giving me a dy equal to 15 times sine 30. Now, to get the specific value of this, we would look at this and say that if I want to get the specific value, and I did this in my calculator, 15 times sine 30 would give me positive 7.5. So I'm going to write positive 7.5 meters. Or we could call this 7.5 meters north if we really wanted to. So I'm also going to put 7.5 meters in the north direction. So that's one way to classify it. To do the dx calculation, we're going to do it off on the left-hand side here. Instead of doing sine, well, we know we have a degree here. We're trying to solve for this side here, which is the adjacent. We have the hypotenuse, so I'm going to use cos. This is going to be cos of 30, which is equal to, and then from here, we're going to say it is dx divided by 15. So dx divided by 15. Now, we're going to multiply up to 15 to both sides, and very similarly, we're going to get a result where dx is equal to 15 cos 30. And if you were to put this into your calculator, what you would get is positive 12.99. And so I'm just going to move that dx over just slightly because we can indicate that it's here. So this is positive 12.99 meters. And again, how else could you answer this? You could say it is 12.99 meters in the east direction. That would also be totally fine for this type of problem here, 12.99 in the east direction. Okay, so interesting. Now we have this idea of some amount in the north direction, which ended up being this positive 7.5, so I'll highlight that. And then in terms of the x direction, we have this as 12.99 east. And when we have a triangle that's composed of these things with the right angle triangle, we now can summarize what this b vector is in terms of a combination of a horizontal and vertical component. So the 15 is composed of this x and y direction that come together at 30 degrees. Now, here's where this leads us into. So if we look at our triangle, based on what it looks like now, they fill in the 12.99 in the east direction. They fill in the positive 7.5 in the north direction. What we can actually do is we can just cancel out the b vector. And the reason why we cancel out this b vector, or we eliminate this b vector, is I want to primarily focus on the resultant triangle that is created now. We have a resultant here, and it's composed of some amount in the x, some amount in the y. And these two things come together to make that nice right angle triangle that makes it very similar to what we talked about in the previous class. Do you see how if we don't need this anymore, this red here, so I'm going to say this is not needed. When this is not needed, we can just go right to our lesson 7 skills. Rather than having to use the laws of sines and cosines, we just use our basic trigonometry that we've done before, where we sum the x components, sum the y components, and solve for this resultant. So doing that below here, if we sum the x components, or we take the sigma x, that means we're going to add all our x components together, and using sines, I say it's positive 20 meters in the x, which was the vector A. Vector B in the east component is positive 12.99. So I'm going to 12.99 meters. There we go. And this is going to give me a combination, when I put these two things together, of 32.99 in the positive direction, 32.99 meters, which you could also classify this as 32.99 east if we wanted to. In the y component, there's only one value. It's positive 7.5. There's no south component, so because it's only one component, we're just going to write it as the sum of the y's is equal to just 7.5. Now, off to our triangle on the side here, what we're going to do is we're going to fill these following values in. On the x component, or the east component, we say this is 32.99 meters. In terms of the y component, we get 7.5 meters. And now this should look identical to what we've done in the previous lesson when it came to lesson 7 using some right angle triangle to solve this. So we're going to solve for this theta here. And on top of solving for theta, what we're also going to use is Pythag in order to solve for our resultant vector. So the resultant vector is equal to, and I'll make sure that I put in the resultant squared, is equal to the square root, and not the square root yet, the square value of positive 32.99. This is meters squared plus the 7.5 squared. Now, in order to undo the square on the r, we're going to square root both sides. And when we square root both sides, we're going to get a resultant vector equal to, and for this one, it will be 34 meters. So the length of this resultant, or the length of the displacement, is equal to 34 meters based on the following criteria where we put these two things together, or these two movement patterns together, to get some sort of overall resultant. Now, as you can see, this is the same thing that we did in lesson 7. You should be recognizing this and being like, hey, this is the same principle that we talked about before, creating a right triangle, using that right triangle to solve for an angle and some sort of overall magnitude. And then what we can do from here is just follow the same steps. Use Pythag to get r, which we just did. Now we can use the tan inverse to find the angle. And then lastly, we can state the direction using Cartesian or navigator methods. And remember, between these, we could get 3 possible answers. So I'm just going to write in that 3 possible answers are possible given this criteria here. Okay. Now, on the next page here, and we'll go on to the first example. I was going to say maybe we solve for the angle here and do that, but in the first example, we're going to do that anyways. So let's take a look at how we piece this all together here. So, and actually, no, let's just show it to be safe with this one. I was going to say we skip it, but let's actually put in the detail here. So I'm going to pop open another page here, and we're going to continue that following problem. So when we go to our next step, because we already have the resultant magnitude, what we want to do is use our tan ratio and go tan theta is equal to, well, on the previous page, we saw this as the triangle said that from the point of view of the angle, which is here, we have an opposite over an adjacent. So 7.5 divided by 32.99. And so let's make sure to put that in here, 7.9 divided by 32.99. And then continuing this, we would say that theta is equal to, we have to inverse tan in order to get the specific angle, inverse of 7.9 divided by the 32.99. Perfect. And then once we get an actual angle from here, we would solve that. Once it's in degree mode and we type this into our inverse, theta would be equal to positive 13 degrees. Now, we're going to put together the 3 solutions that are possible for here. So therefore, the resultant vector is equal to, well, the magnitude was 34 meters, so that's not going to change. In the first set of brackets, though, we're going to do the navigator methods first and then the Cartesian. Navigator method says that this was 13 degrees, and it's going to be north of east because we headed away from the east axis towards the north. Another possible answer could be that we get 34 meters, and then we want to do the complement angle. To do the complement angle, remember, we're going to take this and say, hey, it's going to be 90 minus 13. And so if I do that off to the side here, 90 minus 13 degrees, this is going to give me an answer of 77 degrees as the complement angle. So I'm going to put in 77 degrees east of north because the complement is just the inverse of this, or it is the alternative angle that is in this quadrant 1. So both of these, when put together, these represent the navigator method. And so when we put them both together, there's 2 possible methods or 2 possible answers out of the navigator method. Last method that we can look at is the Cartesian method. It uses the exact same magnitude, but rather you start on the x-axis and rotate to this angle. Because it's a quadrant 1 angle, it's actually just the angle itself. We don't need to do any special work with this. So there is the 3 possible answers. And now, if this was any sort of multiple choice or any sort of assessment, remember, you could see any one of these. In fact, in the practice problems, they love to mix it up and say, hey, which one of these solutions do you solve for, and then which one can you convert it to get the answer that's listed in the solution. So just remember that this could be a possible thing you would see where they may ask for one method over the other, even though you might originally solve for one. And again, two answers for navigator, one answer for the Cartesian method. All right, now let's actually try out some examples on our own here. Decompose the acceleration vector of 25 meters per second squared in the direction of 215 degrees into its perpendicular components. Now, what they essentially mean by this is let's draw this out on a Cartesian plane and then break it apart into the points that represent the amount horizontally displaced and how much it is vertically accelerated. And I'm going to use that key terminology too. Horizontally accelerated, vertically accelerated, because these, when we draw them out, they could be in acceleration, they can be in velocities, they can be in displacements. So far, we've primarily seen them in displacements, but it's possible that we see them also in accelerations and velocities. So for step number one, what I recommend is you always should draw out some sort of basic Cartesian. Now, I'm going to put together the following. I know that the resultant vector ends up heading in the 215 degree area. That means that the arrow or the acceleration is actually pointing in this direction. And if you need a little bit of assistance on seeing this, we know that 0 degrees is here, 90 degrees is here, we know 180 is over here, and we know 270 is down here. And lastly, 360 is when we complete a full circle. So we know that it's going to appear in quadrant 3 here. Now, knowing this, what I can do is actually put the following. I can put a dotted line here representing the acceleration in the x direction, and then by tip to tail vector addition, I have some sort of acceleration in the south direction. Here's how we're going to classify this. Part 1, we need to solve for the acceleration in the x direction. Part number 2, we need to solve for the acceleration in the y direction. If we can solve for these two things, perfect, that's great. Now, we know the overall magnitude of this is going to be 25 meters per second squared, or the acceleration that represents the resultant. So that's going to go on the hypotenuse there. But then you're probably thinking, how do we know what this angle is here based on the description? They told us it was 215. Well, in order to find the theta, what we're going to do is we're going to take this angle and say 215 degrees, which is the total rotational angle, minus the 180 that represents the half circle. This is going to give us an angle of 35 degrees for this theta. So I'm going to write in 35 degrees. Now again, because we're breaking this apart into an AX and an AY, or acceleration in the X direction versus acceleration in the Y direction, I'm going to do those two steps independently below. So step number 1, we're going to solve for the AX. When we solve for the AX, here's what we're going to get. We know that this is the adjacent over the hypotenuse. So I'm going to say that this is the cos ratio, cos of the 35 degrees that they gave us, is equal to the AX, which is the adjacent, divided by the 25 meters per second, which comes from the denominator here. And so I could put this as meters per second squared just to make sure that we're including our units, but realistically, I can maybe live without those. The reason I'd want to put in the units is so that I remember that those are included in our answer. Now, if I multiply both sides by the 25 meters per second squared, that's going to raise that up to the numerator, and it's going to give us the following, that the acceleration in the x direction is equal to 25 meters per second squared multiplied by the cos 35. We now are going to get that the AX, or the acceleration in the x direction, is equal to negative 20.5, and this is meters per second squared. Or we can answer this using directional values. This is 20.5 meters per second squared in the west direction. So this would be the two ways of putting it, is either negative or west. Now for part number 2, we want to solve for the acceleration in the y direction. So I'm going to go number 2. And very similarly, but just using the slightly different ratio, it's now, instead of cos, it's going to be sine. So sine 35 is equal to, we're going to get a of y, or acceleration in the y direction, divided by 25 meters per second squared. I'm going to multiply up the 25 meters per second squared, just like we did in the a of x. This is going to give us a of y is equal to 25 meters per second squared multiplied by the sine 35. And typing this into our calculator, we're going to get ay is equal to, putting this in, just making sure we get the exact magnitude, negative 14.3 meters per second squared, or this is going to be equal to 14.3 meters per second squared in the south direction. just to be very clear here. So either one of these answers could appear. So this is what they mean by break it apart into its components. We now have some sort of component of acceleration in the x direction, some sort of component in the y direction, and when you actually put them together, it gives you this overall resultant in terms of an acceleration in a given direction. But if we want to break it apart, this is a very powerful tool going forward. Okay, now let's look at our final example, or example number 2. This one is quite complex, and the reason it's quite complex is we have this multi-directional displacement going on. And so the best way to do this is anytime they give you a problem like this, where it's like a man is walking 40 meters in some given direction, that's like a component or a navigation method or a navigator method. And then they give you another displacement using navigator, and then another displacement navigator. Rather than writing these all out individually and then trying to do them all on their own, what we can actually do is write out one Cartesian and then overlap them all and then try to solve from there and label them to help us figure this out. Now, let's see what that actually looks like in the following. So I'm going to zoom in here and I'm going to create a Cartesian plane right off the hop here. So I'm going to create this Cartesian plane that looks like this. Now, what we're going to do is we're going to start off with the man's first journey, 40 meters, 60 degrees east of north. So what that's going to do is in red, let's start off with that. It's going to be in quadrant 1. We're going to write in that this is 60 degrees here. So 60 degrees on the interior because it's east of north, or heading towards the east from the north. We then want to break this apart into the components, which there's going to be some sort of north component, so north displacement, some sort of east displacement, and that's going to put us here. Now, to further classify this, I'm just going to slightly move this down just so that we can actually be a little bit more specific with our labeling here. So this is what we're going to have here. On the top, I would like you to write the following. If I know that this was 40 meters in this direction using the resultant magnitude, I'm going to say that this is going to be the VX40, or and we could also call it V40X if we wanted to, meaning it is the overall displacement in that direction. And so rather than the V, I'm going to actually put like D of X. So this is dx in the, and I got to make sure I can put 40 first, 40x. There we go. D40x, meaning the displacement in the x direction for this 40. I could then write in the vertical direction that this would be V, not V, but D 40y. Okay, that's our one triangle drawn out. Perfect. Now what we're going to do is we're going to draw a triangle out in blue for the second component, 70 meters, 50 degrees south of east. 50 degrees south of east, well, that's going to put me on a line where I'm in quadrant 4, so I'll look something like this. The vector should be a little bit longer because it is 50 at the end of the day, so I'm going to write this as, it's 70 at the end of the day. 50 is the degree. Now, I'm going to enclose it with the following. I know that I have to go some amount east to get to this, some amount south, and so using proper labeling, I'm going to make this 50 degrees on the interior here. I'm going to call this the D70X, and I'm going to call this the D70Y, meaning the distance or the displacement in the Y direction for the 70 meter. Now, lastly, we have one more triangle, which I'm going to draw in green here, and it's the 20 meters the man travels 45 degrees north of west. Now, where does that put us? That puts us in quadrant 2. So I'm going to draw a straight line from from the origin into quadrant 2 as following. I'm going to label the magnitude, which was the 20 meters he travels. I'm also going to fill in the fact that we have to go west by some amount in order to get to this. And by tip to tail vector addition, I'm going to head north to get to that resultant. Now, the degree in here was 45 degrees, so I'm going to make sure I fill this in. I want to then solve for D of 20x and D of 20 in the y direction. There we go. Okay, this probably seems super overwhelming, but we're going to break it down one by one until we get some sort of overall sum of the x's, sum of the y's, and let's see what that means. So we want to solve for all of the displacements in terms of the x components. And then once we have all those, we can add them together. Similarly, I want to solve for all the displacements in terms of the y values and add those together, because then I'll get one overall magnitude in terms of how much it goes north or south. So let's start off with doing our x components here. So to get all the x components, maybe I'll do that, yeah, maybe off to the side here. So let's start off by solving for d20x. Well, d20x relies around the fact that we have some sort of angle here, and we have an adjacent over hypotenuse. So we know that this is the cos ratio. So I'm going to say that this is equal to, and I'm going to start short forming it, because when we solve for these side lengths, you can actually do the following: hypotenuse times whatever ratio it's dealing with. So for step number one, when we're talking about getting all the x values, I'm going to say that d20x is equal to, I'm going to multiply 20 meters times the cos of 45. Now, this is going to give me that d20x is equal to, and I just want to make sure I get this exactly right here, this should be negative 14.14 meters. And it's negative because we're heading in the west direction. Now, for my next dx, or my next dx for whatever magnitude in terms of the displacement, let's go to the red triangle here. I want to solve for d40x. This revolves around that I go from the degree opposite over hypotenuse. This is the sine ratio instead. And again, I'm going to use the short form. So I'm going to go d of 40x is equal to 20 meters multiplied by the sine of the 60 degrees. And when I get the value for this one, I get d40x is equal to, and just to make sure that I get the appropriate value here, it's positive 34.64. There we go. Okay, lastly, we want the d70x. The d70x, so I'll make sure I go highlight what ratio we're going to need in order to solve this. If I go off to the side, well, 50 degrees is here. This is our adjacent value. This is our hypotenuse. So I'm going to have to use the cos ratio. So this is going to be, instead of, oh, and I should backpedal this just very slightly. This needs to be 40 meters times the sine 60 on the last one. And then our new one needs to be 70 meters times the cos of the new degree, which was 50. Now, if I get d70x, this is going to be equal to 70 times the cos 50. 70 times cos 50 should give me positive 45.0. And this is in meters. There we go. Okay, now what we want to do is we want to also solve for all the y values. So maybe I'll do that as step number 2 here. Step number 2, we're going to solve for all the y's for each of these. And so we'll go down the list again for starting off with d20y. Well, d20y, if the first ratio was the cos ratio, this must be the sine ratio. So it's going to be 20 meters multiplied by the sine of 45. And as a value here, I'm actually going to get the same thing, but positive because it's in the north direction. So d20y is equal to positive 14.14. Okay, now what we're going to do is the next one. We're going to, and I'll move this over just to make sure I can fit all three of them here. So I'm going to move this to the edge here. Now, I'm going to write below this that we want to solve for the d40y. The d40y means we're going to multiply 40 meters times, well, if it was sine for the x value, then it's going to be the cos of 40. And the specific value for this one is going to be the following. And just to make sure, it's going to be cos of 60, not 40. There we go. Cos of 60. Now we get d40y is equal to, and just to make sure I get the magnitude right here, we get positive 20 meters. Okay, and then lastly, what we're going to do is put together our final bit here. And what I'll do is I'll condense this just a little bit more so we can make sure to fit this here. I thought that would be enough room, but we might need just a touch more. So I'm going to drag this right to the edge here. I'm going to label my step number 2 here. There we go. And then we're going to fill in that last piece. So now d70y is equal to 70 meters multiplied by, if it was originally cos for the x value, then it must be sine for the y value, sine of 50, and therefore I'm going to get d70y is equal to, checking the magnitude, negative 53.6. And this is in meters. Okay, now we have all of them put together here. This seems like a lot, but we've broken each of these triangles down. It's a little bit tedious, and that's the biggest thing I would say about it, is that it takes a lot of effort to break these things down, But once you get in the habit, or once you get in the routine of breaking them down, it actually becomes pretty intuitive. Now what we're going to do on the next page is sum up all our x values, sum up all our y values. And so if I was to outline these here, maybe I'll do that actually quickly before we go to the next page here. What we're going to do is put all of these values together, take them and sum them together. The other values we're going to sum together are all the ones we're going to outline in the pink here. We're going to sum up all our y values. So we're going to take the greens, add them together. The pinks, add them together. Now, on the next page, when we flip this over, we're going to use some pretty formal notation here. So if step 1 and 2 was breaking down the x and y's, now step number 3 is going to be summing them all together. The sum, or the sigma of x, I'm going to try and draw that just a bit better. I know I struggled to draw this one even in class. The sigma of x, or the sum of the x's, is equal to, I'm going to take the negative 14.14 from the first triangle. I'm going to add that to, we have positive 34.64 meters, which came from our 60-degree triangle. And then lastly, from our 70-degree triangle, we have, or our 70-meter triangle, I should say, we got positive 45 meters, 45.0 meters. Now, that means that the sum of all the x's is equal to positive 65.5. There we go. And I'll just make sure I try to repeat this sigma here. There we go. The sigma of x is positive 65.5. Now let's do the same thing, but for the y's. Sigma of the y's is equal to, we have to add all three y's together, starting off with the positive 14.14 meters that we got in the north direction, plus we add together the positive 20 from our second triangle, or our other north measure, plus we had a south measure of negative 53.6 meters. There we go. Now, when we sum these all together, or when we type these into our calculator and add them, the sum of all the y values, or the sum of all the vertical components, gives us negative 19.46. Negative 19.46, and this is in meters. Now, you're probably thinking, how does this help us? Well, again, just like we did in lesson 7, once we had summed our components of x and y, we could actually put these all together to give us some sort of triangle that is representative of the overall displacement of this man. And so here's what we're going to do. For step number 4, I'm going to draw out a basic Cartesian plane and sketch out the sum of the x and the sum of the y. So let's do this here. Okay, if I want to go in the east direction, or positive x direction, that means that I'm going to go 65 meters in the following x direction. And I'm going to even write in the magnitude here. This is positive 65.5 meters. And rather than writing positive, I'm going to write that it is east. Now we go south by 19.46, so we go down in the vertical direction. And so roughly it should be about, about a fourth of the x value. So it shouldn't be as long as in a vector. And realistically, what I could do here is I could even truncate this a little bit more to make it more accurate. So this is going to be our 19.46. And let's erase that just to make sure it's clear, 19.46 meters. And again, instead of writing negative, I'm going to write south, or instead of writing a sign, I'm just going to write the south. Now, our overall resultant always appears from where we start to where we end, or by tip-to-tail vector addition, there is the resultant that we're looking for. And theta will go on the interior, just for now. We will probably solve for all solutions, but for now, that's what it's going to look like. Now, to get all our solutions here, we're going to have to do a bit of Pythag. We're going to have to do a little bit of figuring out what the angles are using the tangent ratio, and then hopefully we can put together all three solutions here. So here's what we need to do first of all. Let's solve for that r value. The resultant, and I'm going to do this all in block again, the resultant squared is equal to, or the hypotenuse squared is equal to, the other two lengths squared, so 65.5 meters squared, plus the 19.46 squared, and that's in meters, of course. Now, if I add these two things together, and then I end up square rooting it to get my singular r, my singular resultant, this is going to be a singular resultant, and let's just make sure I clean that up a little bit. Our singular resultant is going to be equal to 68 meters. Now remember, this is just a magnitude of the resultant. It doesn't tell us anything about the direction. Now it's our responsibility to solve for the angle that's associated with this. Now, using our triangle, I'm going to go up here and solve for the angle with you. So in order to get this angle that's on the interior here, I'm just going to point to it with a green arrow and say that we're going to use the tangent ratio. Tan theta is equal to the opposite, which is 19.46, divided by the adjacent, which is 65.5. Now, if I use the inverse of tan to solve for this, it's going to be the following. And maybe, let's see if I can fit this here. Theta is equal to tan inverse of the ratio above. And maybe what I'll do is I'll just even arrow it down into there, saying that we are taking the inverse of that ratio. This is going to give me a theta value equal to 17 degrees. Okay, so 17 degrees represents that red angle. Now, this is one possible method. We're using navigator method. We can put this angle and its direction and its magnitude for the resultant together. What we can also do is figure out another angle. The other angle I want us to be thinking about is the navigator method angle, or the orange theta here. And then the last angle I want us thinking about is the one that I'm going to list in, let's say, pink here. This angle here, which we call the complement angle. So to solve for the complement angle, what we're going to have to do is say, well, 90 degrees minus the 17 degrees from the original solved green angle, or that original solved red angle, this is going to give us an angle of 73 degrees. So this is equal to 73 degrees, which we can then put down here. This is 73 degrees. To get the navigator method, or the one in orange, we have to say this is 360 degrees minus the original angle we solved in red. This is going to give us an answer of 343. So we know from the positive x-axis, if we rotate counterclockwise around to get to the red resultant arm, we know this is going to take 340 degrees. Now we can put together all our answers based on this. So I'm going to say right at the very bottom here, therefore, the resultant is equal to 68 meters. And then we're going to put in our first navigator method, 17 degrees. If I look at my triangle, it's south of east. We're moving away from the east line towards the south. And so I'm going to say this is south of east. Perfect. I'm even going to clean up that bracket just a little bit because I don't want to make sure that that is a little bit messy there. Now, another solution, again, we're going to take the 68 meters that we got before, but now we're going to use the complement angle, or the angle that was in pink here. It's 73 degrees. That's the alternative angle to this quadrant. So I'm going to say that it is 73 degrees. Really nice thing is we just swap our variables. It is now moving east of the south line, or heading towards the east from the south. Lastly, we want to put in our Cartesian method, which is 68 meters, and it was the one with the large degree, 343 degrees. We don't require any sort of east of south or south of east. So if we were to classify our final answers here, you say that these two comprise the navigator method, just to make sure that we're being specific. These two are your navigator. The one at the very bottom here, this is your Cartesian method. There we go, Cartesian. Perfect. And again, could you guarantee that any particular one of these would be on a multiple choice or any sort of assessment? No, but in terms of, let's say, a written response, or let's say it was a some sort of multiple choice, you might see one answer over the other, or be asked to do one answer over the other. So just be aware that there is 3 possible answers total. That is the number one thing you got to remember, that there is, in the navigator, you can deal with one angle or in the complement angle, and then Cartesian, you have to rotate from the positive x-axis counterclockwise until you reach the resultant arm, and that represents the angle that would give you your solution. And this 68 that appears out front is purely the magnitude of the displacement, the velocity, or the acceleration, depending on what they're asking for. All right, you will definitely need to practice these ones in your practice problems, so please complete all the homework on this section.